Hello all, I'm Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. And today's lecture series, we are going to discuss about Kirchhoff's law in DC circuits. Okay, first introduction to Kirchhoff's law. Here we are going to discuss about the history of Kirchhoff's law, introduction and types of Kirchhoff's law. See here, German physicist Gustav Robert Kirchhoff, he found Kirchhoff's law. Here, he described two laws that became central to electrical engineering in 1845. The laws were generalized from the work of George Ohm, but it can also be derived from Maxwell's equations, but were developed prior to Maxwell's work. See here, what is this Kirchhoff's law? How it is derived? A pair of laws stating general restrictions on the current and voltage in an electric circuit, it is called Kirchhoff's law. The first law, it states that at any given instant, the sum of voltages around any closed path or loop in the network is zero. Second states that at any junction of paths or node in a network, sum of currents arriving at any instant is equal to the sum of currents flowing away. See here, KVL is Kirchhoff voltage law and KCL is Kirchhoff current law. See. Here, next one is introduction of Kirchhoff's current law. Kirchhoff's current law is sometimes called Kirchhoff's first law or Kirchhoff's junction rule. And here, it will be shown how Kirchhoff's current law describes the current flow through a junction of a circuit. Along with Kirchhoff's voltage law, makes up two fundamental laws of electrical engineering. See here. KCL helps to solve unknowns when working with electrical circuits. KCL with the addition of KVL and Ohm's law will allow for the solution of complex circuits. See, actually, what is a junction? A junction is any point in a circuit where two or more circuit paths come together. See the example. See the first one. Here, the arrow denotes the junction. Same, the second one. It is a junction. A junction is any point in a circuit where two or more circuit paths come together. See, the algebraic sum of all currents entering positive and leaving negative at any point junction in a circuit must equal 0. See here summation In, which is equal to I1 plus I2 plus I3 plus I4 equal to 0. See here sum of all currents entering and leaving any point in a circuit is 0. Here I2 and I3 are entering and I1 and I4 are leaving. Here the sum is 0. See, the sum of the currents into a junction is equal to the sum of the currents out of that junction. See here, the algebraic sum of all currents entering and leaving any point in a circuit must be equal to 0. See the example. Here, three currents entering the node I1, I2, I3 are all positive in value and two currents leaving the node I4 and I5 are negative in value. Then, this means we also rewrite the equation. See here, I1 plus I2 plus I3 plus minus I4 plus minus I5. It is equal to 0. Currents entering in the node equals currents leaving the node. See, next one is nodes analysis. Analysis using KCL to solve for voltages at each common node of the network and hence determine the currents through and voltages across each elements of the network. See, node analysis procedure. Here, see here, first one is common node. Determine the number of common nodes and a reference node within that network. And second one is current direction. Assign current and its direction to each distinct branch of the nodes in the network. Next one, KCL. Apply KCL at each of the common nodes in the network. Solve the equation. Solve the resulting simultaneous linear equation for the node voltage. And finally, determine current and voltage. Determine the currents through and voltages across each elements in the network. Node analysis procedure. First one is determine common node. Second one is current direction. Third one is KCL. Fourth one is half equation. And fifth one is determine I and V. See here I have some exercise. See first example, find the current flow through each resistor using node analysis for the circuit below. See here voltage V1, R1, here the resistors are R1, R2 and R3, voltages are V1 and V2. See first one, determine the number of common nodes and reference node within the network. We have one common node VA and one reference node C. Second step, assign current and its direction to each distinct branch of the nodes in the network. Refer figure. Next one is apply KCL at each common nodes in the network. So I1 plus I2 it is equal to I3. See here the equation becomes 10 minus VA by 10 I1 plus I2 20 minus VA by 20 which is equal to I3 VA by 40. By solving this equation, we will get 1 minus VA by 10 plus 1 minus VA by 20 equal to VA by 40. Again, we will get VA as 11.428 volt. See here, apply this VA value in I1, I2 and I3, we will get. Apply this VA value in I1. What is our I1 value? 10 minus VA by 10. Apply VA equal to 11.428 in 10 minus VA by 10. You will get minus 0.143 ampere. Second, apply this VA in I2. 20 minus VA by 20. You will get 0.429 amps. And I3 will get VA by 40 will get 0.286 amps. By solving common nodes and current flow direction, we will get the VA value and substitute this VA value in I1, I2 and I3. We will get the current across the node I1, I2 and I3. And see the example 2. Find the current flow through each resistor using nodal analysis for the circuit below. See here. Here our current value is 40 minus VA by 5K and which is equal to VA minus 55 divided by 3K plus VA by 6K. Here we will get I1 is 10.95 and milliamps and I2 is 13.41 milliamps and I3 is 2.46 milliamps. That's it. Thank you.